The HA4A is our workhorse, but we have a smaller version of that, the HA2A and 2B. Then we have other options like this, EM motorized valve, piston that we have, and then we have three-way valves for like thermal siphon oil coolers or water diverters or whatever you're using. So the HA4A is 3/4 to 6 inch or 4 inch flange, and then 5 and 6 inch welding line. And like the solenoid, there's a manual stem, and it's on the top. You'll see the similarities between the solenoid and these regulators, because they pretty much have the same bodies and V-ports and stems and stuff. Again, we have various models. We do pressure and temperatures and the inlet and outlet and differentials and outlet pressures and all kinds of stuff we can do depending on what kind of modules and setup we put on. We have different pressure settings for the modules, so we can do down to 20 inches vacuum, get to low temp, and then up to high pressures, 450 and 300 if we're doing something at higher pressures. We can offer shutoffs or wide opens or dual features. We'll show you how all those work. And like the other solenoids, same type of working temperatures and pressures. 400 for ammonia, minus 60 degree Fahrenheit on the low end. So if you look, right, I mean, this is our solenoid body and V-port, spring, piston, manual stem, cap, all this stuff remains the same. The only thing is we're doing different is we're putting in a pressure module here. That's the only difference, right? So these parts are all interchangeable between solenoids and pressure regulators, with some differences, some slight differences on port sizes and stuff we can do. The HA4A is kind of our standard bread and butter inlet or back pressure regulator. So it's going to control the pressure on the downstream side. And we put these, again, pressure modules in them. We make two different styles, M3, which has bolts on here so we can replace diaphragms and springs and surface them. And the other three is a welded type of module, pressure module, and you can't service it, they just get thrown away. What?
Direct replacement.
Yeah, direct replacement. And most of the time, even these ones, people are just replacing. By the time you get it apart and spend your time and money doing it, and ordering parts and shipping them in and doing everything else, I see a lot of people who just buy the whole module. They just get a fresh start, fresh coat of paint. So the back pressure regulator works simply, again, high pressure is on this side, lower pressure is on this side. My evaporator pressure, for instance, and my house suction pressure. There's some pressure difference between them, which I need to overcome at spring pressure, 2 to 4 pounds. But again, we're bringing pressure to the top of that seat here, right? But instead of it having like on and off, right, with the solenoid, thank you. This has a spring pressure on it and a diaphragm. So that diaphragm with the spring pressure is making a tight seat up here. Once we start building pressure on this side, it raises the pressure, it overcomes the spring pressure, and the diaphragm cups, right? Once the diaphragm cups, we can get gas down to our piston area, and then we can start modulating depending on how far the cupping action is going, if it will go open and close or somewhere in between, to maintain a steady pressure on this side. So pretty easy, right? Once you see it, we got a spring pressure, we can change that spring pressure, loosen it for lower pressures, tighten it in for higher pressures, right? So when we set them up and we want to know what pressure we're going to maintain this back pressure at, we need some type of gauge to tell us, or some type of pressure indicator. Maybe you got a transducer in a computer system, but you'll need something to tell you what this pressure is at, because you want to set these turns in or out based on what this pressure gauge is doing. So we provide a port on the valve, a gauge port, and normally gauge is on, a gauge valve is on it, and then a gauge. And you can watch it, right? If you turn it in and out, you can watch the pressure change on it. The HA48K is very similar, but it's going to hold on back pressure. But this is the valve we use in a defrost relief. Those application drawings we used. This is the one that's going to hold back the evaporator at 70 pounds is our standard pressure setting. And so it doesn't get tampered with. We provide a seal on it, so it stays at 70 pounds. Someone's not changing my defrost pressure up and down. But same type of operation, right? We've got a gas pressure. Once we build up to 70 and higher, it will start opening, and then we can regulate it to keep it and maintain it at 70 pounds PSIG. A differential regulator, the L, again, we want to maintain some type of pressure difference across the valve, right? And I remember, because we haven't worked at Velter in my car, we use a lot of them on screw compressors. You know, your screw compressors used to have oil pumps, now a lot of them don't, but back in the day they had oil pumps. You build up oil pump pressure, but then you want to maintain the oil pressure going to the seal and bearings and the slide valve. And I mean, usually about 35 PSIG, and the pump might put out 60, but the pump might put out 60 PSI. So we'd have these differential regulators that would flow high pressure oil, and then the overflow would go back to the separator, and then we'd have 35 PSIG going down to the screw compressor. But you could also use them like in a pump application on a recirc if you want to just maintain a 35 PSI going out to any recirc valves in a valve train. But here's how it's going to work. You got because we want to maintain this differential. I got an input signal on this side, right, from this side. This pressure's here, but I need some outlet pressure to tell me what's going on the other side of the diaphragm, because I want to maintain the difference here the same over here, right? So spring pressure plus outlet pressure is going to put a force on here. Then I can measure what my differential is, right, across it. So on this one, you'll probably want to have something measuring downstream. Back in the day, again, oil line pressure transducer to let you know what this differential pressure was. But that's it. It would have tubing on it. You're kind of familiar because it has a tubing on the outlet side. So it's either two types of valves. We use tubing on the outlet pressure regulator. I'll show you that later. And this differential regulator have tubing on it. So here's the outlet pressure regulator. So this one's a little more complicated, right? So I'm not really care what's going on here. I want to maintain this pressure. So a good application for this valve is you are taking hot gas, and it's your main feed valve to all your hot gas distribution, right? So I don't want to have hot gas coming right at my condenser pressure, whatever, 180 to 150 PSIG. I want to maybe maintain it at 100 or 110 PSIG going out to my hot gas feeds, right? And stuff. So this would be the kind of valve you want to use to maintain this outlet pressure. So a little different here, like the other valve with tubing. I got an input signal. I don't really care because again, if it's on my condenser, the condenser fans could be going on and off, or water turning on and off, or whatever. Now not as much. But back in the day, we had VFDs driving now, and everything stays pretty still. Condensers loud. Back in the day, you go from Wisconsin with a cold winter day down to 110 psi. You're barely using this valve down to 185 in a hot summer day. But I don't really care what's going on here. I really care what's going on here because I want to maintain this, right? So this is going to supply my high pressure to open the seat, but I really care what's going on here. So this one works kind of reversed versus I got high pressure coming here, and it's not working on the diaphragm up here. There's a space here, and there's a little valve seal here, right? So that valve seals it from going to the top of the piston. So when my outlet pressure drops, right, it keeps it seated, right? Or no, as the outlet pressure drops, it pushes this, what I call the barbell down. There's a little spring here, and it pushes it down, and then it opens up. My gas comes down here, pushes my piston down, and I start building up pressure on this side, right? As my pressure goes too high, right, the diaphragm is pushed up, this takes a seat, and then my valve closes up again. So a little different. I mean, this one you'll notice it has the pressure, you know, this big piece in it. It's not just right on, it's a bigger module than our other standard pressure receiver pressure modules, and you'll notice that it has that tubing on it, right? So it's pretty recognizable as an outlet pressure regulator. So here it is, right? We get gas coming up here, we're pushing the barbell open, gas comes to the top of the piston, and I can start regulating that outlet pressure. That's the one I want. There we go. Nope. That one, right there. So on the outlet one, our normal gauge position would be right here, right? You know, if I put a gauge in there, I'd be reading this pressure, not my outlet. So if I'm changing this in and out, and I'm looking at the gauge pressure here, it doesn't tell me much, right? I just had a customer do that. Told me he had 2 of these valves on the roof, high gas line application. Neither of them work. I said, send me a picture. Talk to me about it, right? So he sends me takes a photo on his camera, and he's got the pressure valve here. I said, well, you can't tell what's going on here because you have the pressure valve here. The first thing I told him, it's wrong. No, it's working, and your valves are just bypassed, and we can't set them up and stuff. Well, okay, you need some parts. Let's look at what's going on here. Let's look at what's going on here. You're gonna have to take it apart. No, we don't want to take it apart. We gotta, buy new valves. Talked to his boss and said there's not a whole lot technical wrong with these valves, so they're brand new. You use a manual stem to open them and close them. We want new valves. We want to just get it done, cut them in, we'll put a new valve in. So when we get these valves back, returned, and they work fine, you're not going to get credit for them. You're going to have them keep them at your shop, right? So we send them out. We get a call. They're still not working. All your valves suck. And I'm like, oh geez, what's going on? Call them up. Say, well, same type of symptoms. You got the valve gauge in the right spot? No communication. We're texting. He says, I'll tell you what happens. So a couple days later, it's working. So, what was it? What was it? Let me learn too. What was it? No answer. Okay, well, how did it work? No answer. So I talked to his boss and another thing. He said, well, what happened to the job, to the outlet regulator? He says, oh, you got to work. The gauge was in the wrong spot. We were reading down. We weren't reading the right pressure. And I said, "Don't." I told him that the first thing when I saw the pictures, I told him that. He's like, "Yeah, I know. We didn't want into it. We didn't want into it." I'm like, "Oh, hard lesson. Cost him some money." The M is a motorized type of electric compensated motor. I don't know why the picture's not coming up on that one. Anyway. But it basically has a motor with a cam on it, which drives the pressure module. Rather than turning it in and out, it's got a direct drive on it. And the cam turns and drives the pin on the pressure module up and down, so it can change the pressure setting on the pressure module. We sell these regulators, the R1 and the AR3, A1 being a 1-port, the 3 having 1, 2, 3 ports. To people who maybe want to put their own, hey, I got this in stock, I can put the pressure module on it, I can put a solenoid, it's ready, I can ship it that way and get some, variation of what I hold stock. They're available. But also, just to point out, the 3-port one, we have a parallel port. It's parallel to the piston. Then we have a series. We got 2 ports in series here. So we can do different stuff, and I'll show you some of the stuff we can do with these ports. So we can have a valve that we want to regulate, and a B, a wide open feature. So here's how that works, right? We got a valve, set up. It's got the 3 ports on it. When we energize this coil, it acts just like a solenoid, right? gas, high pressure gas or liquid coming there, it goes right to the top of the piston, goes wide open, right? If we want to regulate it, we de-energize the solenoid. Rather than it going this way, it's not going to flow, so it goes through this way. It's to our diaphragm again, and it starts to regulate and open that piston, or push on that piston up and down to regulate. So energized solenoid, de-energized regulator, wide open feature. The other side of the coin is if we want to shut it off, electrically shut it off, right? So here, rather than it being a solenoid over here, we plug this hole, so it's only got one path to go. So when we energize it, it goes through there and it acts like a regulator, right? We want it to shut, gas can't go through here and get there, gas can't go through here and up here through it, so we energize it, it acts like a shut-off valve. Just like a shut-off, not a shut-off valve, but a solenoid shut off, right? Because we're not getting any gas or liquid to the piston. So that's where a case where we're using, you know, these three modules or three ports to do different types of actions, right? So knowing that, we can do more stuff, right? But in those instances, we choose two different types of plugs. One was a stopping plug, and one was a through plug. We'll just go back here. So this one used a stopping plug, right? It's not stopping gas from going through there. This one uses a through plug. It's short, it doesn't see here, and it brings it through here. So you can identify, if you see these on a valve, a stopping plug has four sides. You know, a straight through plug has the hex on it. And plus they're marked, stopping, hold, through, they're stamped on the sides. So this is a pretty common valve. It's a dual pressure regulator. So it's going to operate at two different pressures. One, a low pressure for like an evaporator, right? If I'm using a standard evaporation mode, I can use a low pressure regulation on it. And then if I want to go into defrost, I can use a high pressure rating to build up the pressure in the coil to get the frosted stuff off. So you'd normally see a dual at moderate temperatures, 32 down to maybe 0 or 10, somewhere in that range. Maybe not much lower than that, because again, what you have to overcome this pressure drop. The lower in pressure you go, the more penalty I pay in horsepower for overcoming that 2-pound drop. So let's see how that really works. But again, here, right, we're starting to get all three of those modules doing something. So in this case, the red is our high, our supply side, right? Evaporator pressure. It's not going through here. It's not going through here. Not much is happening there. Well, it stopped here, right? It's getting up to that piston. But here, once we, well, that's the same picture. Let's just look at this one. If I want to run it at low pressure, I'd open this, and then I would supply pressure to the top of the diaphragm. It cups as I build pressure up, and it wants to lower it. It starts feeding gas to the top of the piston, and it opens and closes to regulate it at low pressure. Once I want to go to high pressure, I seal this off. Low pressure can open here, and I start building pressure until I get to a high enough pressure where I can cup this piston, and then it starts feeding to the top of the piston and regulating at this higher pressure setting. When you recognize these valves, it's kind of the high pressure is always on the inlet side. The low pressure is always associated with the solenoid. I won't spend a whole lot of time on capacity charts. But, I mean, when we just look at a port, when we think about pressures across the port, right? Time for a chalk talk, all right? We got a fixed size orifice, right? 3/4 inch, 1 inch, whatever it is. So if I got a 2-pound pressure drop, right, the change in pressure across the port is gonna influence how it operates, right? If I got 2 pounds, I get some flow through, right? You know, 2 pounds, some flow. I go up to 3 pounds, I get more flow, right? Keep going higher and higher, pressure increases across the port, more and more flow, right? Through it, more and more and more and more flow. Essentially, you get to a point where I can't cram more through it, right? It chokes itself, right? I can't, even though I'm going higher and higher in pressure, unless again, okay, you can make rockets, right? That's what we do with rockets, right? We have some source here, real high pressure, and we have a nozzle here, and then it comes blasting out here. That's not refrigeration. But we limit it to choke pressure at relatively reasonable velocities to get to a point where, hey, we're not gonna try to shove more through it because my line velocities and everything would have to increase way beyond what the capacities we need them to do. But that's principally what it is taking, right? So if I increase my pressure, I can get more tonnage out of the thing, right? So say I'm somewhere here, 5, I got to 20 ton, right? At 0 degrees, and I got a 5-pound drop across, boom. I can go with this one. Well, I could go a little more, bigger size, and get a 2-pound drop. Well, if I'm gonna run my compressors from 2 to 5-pound difference in pressures, my suction pressure, right? The more difference, the more horsepower I gotta put in the cycle. I might be saving money, I might pay for a bigger valve, but I might be saving a lot of electricity over the lifetime of the valve by putting that 3 less pounds of suction pressure on my compressor. So that's kind of the way the tables work, right? I increase the pressure difference. So if you ask me, what's the application? The first thing I'm going to tell is, what's the pressure inlet? What's the pressure outlet? What kind of condition is this liquid? Is this gas? So then I get numbers, right? I'm an engineer. I got to have numbers, right? And then I got more questions, and then more questions, and more questions, and more questions. You guys work with engineers before, right?
The more you try to force through that valve, the more you damage it, correct?
Well, yeah, you can get to a point again, especially with liquids, right? If there's pressure difference, you get flashing, right? And that's not what a solenoid's for. We have an expansion device for flashing. But yeah, again, you can get some erosion, right? I mean, you force a liquid through fast enough, you're going to get stuff happens quick, and we don't want it. Like I said before, we don't want quick stuff in our refrigeration. Slow and steady is great for us. Fast is hurry into making mistakes. Trust me, as an engineer, I know that. That's life in principle, I know. And, like sometimes with my wife, keeping my mouth shut would have been better than rushing into something I said. Anyway, but the sizing right now, you're not going to size a port based on, the pipe size, right? That could be principally totally wrong. You end up with all your valves oversized. But yeah, he's Joe's Heating and Plumbing. Next week, he's ammonia refrigeration and plumbing, right? I got 6-inch line sizes, give me 6-inch regulators. Well, Joe, you might be your own worst enemy, right? But anyway, too, a regulator should work really good at reduced loads. 15%, is no problem up to full load. You get bigger valves, where you get real light loads, less than 15%. You may have, chattering because it's always going, it's high, low, high, low, high, low. And the piston, and the coupling diaphragms going like this, and you hear a valve chattering. That's because you might be operating, somewhere a real light load. And like I said, in general, solenoids and regulators, we're going to need that 2 to 3 psi minimum to reliably open the valve and overcome the spring pressure. Causes of failure are kind of similar to the solenoid, right? Debris on the bead port, we can Teflon, we've got issues there. Debris of the passages, same thing, no go to the top of the piston, that's an issue. Debris in the piston ring here, and then slugs, if you break stuff, they don't work. So here's this is my piston, this is my Teflon seal, or I call it lip seal, and this is my cylinder wall here, right? So and when you take apart a solenoid or a regulator, you're gonna wanna, take this off. First step number one, push it up and down, make sure moving is traveling. You're gonna check the sidewalls. You're gonna check the sidewalls of the bore, make sure there's not scrap, debris, stuff going on it there. You're gonna check, you're gonna pull the V-port out and maybe the piston, probably the piston first, right? Take the piston out. You'll wanna check, again, when you look at it, right, this is the leading edge, the trailing edge. You'll check the leading edge, see if it's scuffed up or anything's causing issues there. And then you're gonna look at the lip seal. Is this all packed with debris and stuff? Is it rolled? Is it cut? All those kind of things that would, reduce the sealing. If I'm not making a good seal, I get gas coming around it, and then I can have it not positioning in the right point that I needed to, either hanging up with debris or, just partially opening because it's not getting a seal enough to open it fully. So again, if there's dirt in the seal, you can clean it out, get it to a dip tank, some compressed air in it. It should get the dirt and stuff out of it, and then you should move freely around it. Check it all the way around, make sure it's, like I said, not cut or anything. Yeah, we're gonna, make sure that the disassembled, it's isolated, and refrigerant is moved, all good safety stuff. Speaking of safety, okay. And I meant to start with this, two things, right? If there's a fire alarm, right, the doors are right over there. We gotta get out of here, right? And then the restrooms, I think we all found those a minute ago, but sorry I didn't do that earlier, I meant to. The HA, 2A, and 2B are small pressure regulators, and they can come in sizes 1/4 inch and 3/4 inch flange. But we'll see that, there's a pilot duties or small capacity application. You'll see there's just a small port, and we'll show it in the cutaways. But they can get some different functions on them. Again, we got a gauge port in them so we know what's going on. We can close couple them, like the solenoids and the other bigger regulators. We can close couple them so we don't get debris on. Same type of working temperatures and pressures as we had before. Again, a big one is our inlet pressure, back pressure control. Diaphragm lifts off the seat. So this one, the diaphragm is right on the seat of the body. So there's no pilot operation. It's kind of like the direct solenoid. This one, the diaphragm sits right on the seat, and then when it cups, gas starts moving, or liquid, or whatever we're trying to regulate, starts moving through it. We got high flow, the 2A at different ranges, and then 2B, light loads, but different settings we can regulate at. And then like the defrost regulator, we can have a BK that would regulate some type of back pressure constant. Reseating kind of is what we call those K, reseating regulators. And typically, if our factory setting, like the defrost is 70, otherwise you can tell us a different pressure if I'm putting it on a pump or something. You can tell us, hey, I need that 35 pounds, we can set it up and seal it so it's not tampered with. And then again, a differential, so we have to have an outlet going to the top of the pressure module to maintain that differential. But same type of concept, the diaphragm is right on the seat.